Take down, please. Take down. Let's look at thermodynamic properties of fluid. Take down, please. Thermodynamic properties needs to be considered when a fluid is influenced by change in temperature. Thermodynamic properties needs to be considered when a fluid is influenced by change in temperature. Full stop. Change in temperature. Full stop. The characteristic equation for a perfect gas. The characteristic equation for a perfect gas is given by PV equal to mRT, bit of thermo. The characteristic equation of a perfect gas is given by PV equal to mRT, where P, let's define terms, where P is absolute pressure, of course, in Newton per meter squared, in Newton per meter squared, or Pascal. V is volume in meter cube. N is equal to mass of gas in kilogram. R is characteristic gas constant. Characteristic gas constant. That is kilogram Kelvin, and then T is absolute temperature. Absolute temperature, of course, in Kelvin. Okay, so we have to in Kelvin. That's K. Some simple concepts. Please. Some simple concepts, yeah? What is this? Let's just play with some minor equations. First of all, we said from the characteristic gas constant that PV is equal to mRT. If I divide both sides by volume, becomes this all over volume, this all over volume. Obviously, this will cancel this. That means the absolute pressure is equal to, if I take these two as one, becomes M over V dot these two here, RT. Now, if you remember from our first class, what we did, properties of fluid, we said got something called the mass density or specific mass, which is rho. We said is equal to what there? Mass over volume. Replace this one here. It means that pressure is equal to, this becomes mass density, it becomes rho RT. Let's make mass density subject of the formula. Divide there by RT, divide there by RT. This cancels this. So we have that mass density in terms of thermodynamic properties of fluids is equal to pressure all over characteristic gas constant times temperature. Alright, so I think that's our first equation, please. Mass density is equal to pressure all over this one here. So we have this. If you're done, please, let's proceed. Wait for you, please. Copy down, let's proceed. Just pinpoint some stuff that we should note, and then we can move on. Notice, please. Notice, please. Note that universal gas constant, let's call this R naught. is equal to N times R. Note that universal gas constant R naught is equal to N times R. We said R is characteristic gas constant. Please, R differ depending on the kind of gas given. Alright, once having the problems, you will get, but just be noting these things first. Alright, if the gas is carbon dioxide, it will have a different R value. If the gas is hydrogen, it will have a different value. Alright, so the characteristic gas constant is specific depending on the kind of gas given. But the universal gas constant is a constant, like it's a general constant. More like saying, what M? So M, please take that. M is equal to molar mass. Molar mass. Right. M is equal to molar mass. If R naught is a constant, what's my value? Please take that. R naught is equal to 8314.3 Newton meter per mole Kelvin. Right. Newton meter per mole Kelvin. So I have this. Well, let's see if this works as I want it to be. From here we said R naught is equal to molar mass times R. Okay, if that's true, let's make R subject of the formula. To make R subject of the formula, I'll divide here by molar mass, divide here by molar mass. This cancels this. So it means that R, which is specific characteristic gas constant, is equal to universal gas constant all over molar mass. Please note this formula. Now, here's the idea. Here's the idea. If I'm to impute this, look at it. If I'm to impute this concept into this my equation here, if I'm to impute this concept into this equation here, it will mean this. It will mean that PV, we said, is equal to mRT. Alright. So from here, it means that PV equal to M, so it becomes M dot, we said R, universal gas constant, is equal to, we said, is characteristic gas constant, R naught all over capital M. So this is mass, this is molar mass, please don't confuse them please. This is mass, this is molar mass times temperature. So I have this. That will mean this. Alright, so from here, I have that PV is equal to, I can take mass over molar mass because it means something in chemistry. Mass over molar mass is what there? Mole. Have it? Yes. Number of mole of the gas is equal to the mass of the gas all over what there? Molar mass. So from here, PV is equal to, I'm taking mass all over molar mass times universal gas constant times temperature. So I have this. But I know that number of moles, N, is equal to mass all over molar mass. So I have this. If I replace this one into this, I'll have that PV is equal to N R naught T. So I have this. So please note these two formula and see the difference. PV is equal to mRT or PV equal to N R naught T. Alright, if I'm working with characteristic gas constant, I'm using mass. If I'm working with universal gas constant, I'm using mole. So please get this difference. So note this formula. So I have this. The pressure and temperature of carbon dioxide, that's CO2. the pressure and temperature of carbon dioxide, that's CO2, in a vessel is 600 kilonewtons per meter square in bracket absolute and 30 degrees Celsius respectively. Alright, find its mass density, comma, specific weight and specific volume. Find its mass density, comma, specific weight and then specific volume. Alright, let's get this done, please. Solution. First things first. What's the question you're giving there, please? Given. Hang on. Given. What's the question you're giving there? Absolute pressure. So P absolute. What's the value? 600 kilonewtons per meter square. What else are you given? Temperature. Let me just use T. Temperature, how many? 20 degrees Celsius. Please convert 30 degrees Celsius. Please convert to Kelvin. That's equal to 30 plus 273. And that's equal to 303 Kelvin. What next again? What is our given there? Okay, that's all. The gas given is carbon dioxide. It has no value. Does it have any value? No. Alright. I'm asked to find what I was given. Mass density rho equal to unknown. What again? Specific weight. That's W equal to unknown. What again? Specific volume. That's V equal to unknown. So how do I find this? What do I do? Listen. I've said before, I said, whenever it comes, listen, I've said before, I said, whenever it comes to a question like this, first of all, think out what you have to do. It will give you a clue on what to do first and what to do next and etc. I'm asked to find specific mass, specific weight, and specific volume. In fact, everything here hinges on my ability to find this one here. Because I know that what specific weight, this is equal to what there? Specific mass times what? Gravity. This is a constant. So if I get this, I get this one too. Also, I know that specific volume V is equal to what there? The inverse of mass density. So this question here hinges on my ability to get the value of specific mass. Now, how do I get specific mass? Check what I give you there. I said rho is equal to what there? P over what there? RT. This R here is what? Characteristic gas constant. Okay. Please check. Do I have P there? Yes. Do I have T there? So if only I can get the value of R. Do I have R there? No. Can I get R? Yes. Check. I don't have R there. So my task now is to look for a way to get the value of R. So how do I get R? Now, hang on, by the way, please. The concept is this. They said this is an absolute pressure. Do you know the types of pressure? Huh? And that's. What if this one was not absolute? What if this was the gauge pressure? What do you do? What if it's standard atmospheric? What do you do? What if it's atmospheric? There are 5 types of pressure in fluid. Okay. No one. It's absolute for now. When it comes down, tell me what to do. Let's get R, please. Let's get R. How do we get R? What's your relationship there? R naught is equal to what there? N times what? R. So that's it. And we said R naught is a constant. We said R naught is equal to what's the value again? 8314.3. So here's my task. Look at it. This one is a constant. Alright, so I have R naught as this one here. My task now be get molar mass. That's it. Get molar mass. So my first task is to find molar mass. Let's get molar mass. Molar mass, that's M, of the gas here is what? CO2. Please, what's the molar mass of CO2? For carbon, what's your atomic mass? 12. Plus oxygen, how many? 16 times number of atoms, 2. So who may remember this from chemistry? They may not give you. They may not give you. So don't forget this. Carbon, the atomic mass is 12. For oxygen is 16. I have 2 atoms. So if they give you a particular gas, you're able to remember how you get molar mass. That's it. This will now be equal to, I have 12 plus 32, and that's equal to what there? 44. Molar mass is measured in gram per mole. No, don't stress. 44, that's the value of N for CO2. So therefore, from here, we can get that R, characteristic gas constant, is equal to universal gas constant all over this for the given gas, which is CO2. I'll have this. So this is now equal to, this value is 831413 all over. The calculated molar mass is 44. Please give me value. 188.96. So I have this value. If I have this now for CO2, then I can now get the mass density. So therefore, number 1, mass density, that's rho, is equal to P all over RT. So rho is equal to P. This one here, please observe, is in kilo. Kilo, that becomes what? 600 times 10 to the power 3 all over R, which is this 188.96 times T, 303. Alright. So T, 303. Give me final answer, please. What do you have?
Why did we use 8.14 as our universal gas constant?
It's a constant now.
I thought you used to be 8.314.
For this one is 8313. I know I took that stuff.
What is the difference? Because I really need that.
It's based on idea of kilo something. This is the idea of kilo. That 83 something is times something. It is in kilo something.
It's not 8. Normally,
Check now. Check. But for this one is 8314. I know we had this same issue last time. So if you have a text, confirm your text. What is text is 8314. The idea is, I think the idea is what's it called? This check. What was the unit for this check? What was the unit for this? I give to you.
You gave us joules per meter.
Just by what? No.
Newton meter
By what? Newton meter per what? Mole Kelvin. So listen. Here's the concept. This is Newton. Newton is for force. Force is equal to mass times acceleration. Now listen now. Mass is going to be what? Kilogram times acceleration, meters per second squared. Now here's the idea. In Newton, the mass there is in kilogram. If you can recall from chemistry you what would be molar mass? Molar mass is measured in what there? Gram per what there? Mole, not kilogram per mole. So it's from here to convert this man here. This one here is in gram per mole. This one here is what there? Kilogram. So because of this kilogram, because to convert it to what gram, multiply by what there? 1000. That's the idea. So you move from that 8.314. From there to convert from kilogram to gram, multiply by 1000. And that's how you get this one here. No, I said don't bother. So this one here is from the idea of I want to convert Newton, which is kilogram, to gram, and this one. That's it. It's okay. Okay, what do you have here, please? 10.48 units. Huh? This one is measured in what? Kilogram. Meter cube. It's not gram, it's kilogram. So kilogram per meter cube. What's next in number 2? You have to find what there? specific weight, this one here, is equal to what? Mass density times what? Gravity. That's equal to 10.48 times 9.81. Please give me value. 102.81 units. So meter cube. Okay. Yes. Yes. We said this is equal to what? Weight over what? Volume. Right. Weight over volume. So Newton per what? Meter cube. One last one. One last one, please. I. Specific volume. Specific volume. We said this is equal to the inverse of mass density, and that's equal to 1 over 10.48. Please give me value. 0.095 units. Meter cube per kilogram. We say is volume over mass, the inverse. You have this. All right. Any questions, please? That's it.